Um, okay, class. I am not a co-host because I can't share my screen. So probably we got, oh, okay, I can see my screen now. Thanks. So, all right. Can you hear me and also can see the screen? So is it you can hear me and see the screen, right? All right. So just now we actually stopped at the binary searching tree. So this is the time constraint. I'm not going to show you how that the binary search tree can actually work, but later on that the codes I've already prepared. So probably you can actually refer to that when it's actually shared to you. But anyway, you can actually find a lot of information online about the binary search tree. So one purpose that I want to say is what is the purpose of binary search tree? Basically, it is actually to have a fast searching. But just now we have actually talked about when your data is actually arranged in a tree form. So let's say you try to search for the A, then you're actually going to the roots of H. So how are you going to do the searching? That you will need to have to arrange your data in certain patterns and also do the searching into a certain patterns. Remember that when you're doing the tree, either you travel to a tree or do the searching, it's always to the left, then to the right side. Okay, so let's quickly go to the graph. So what is graph? Basically, it's a graph is non-linear data structures which consists of two sets. One is vertices, set of nodes, and another one is edges, set of the connections, interconnections between the vertices. When we look at tree, it is arranged in the data is actually arranged in the hierarchical form. But when it's in graph, it is not in hierarchical form. It can be in hierarchical form, but it will be more on like just the connections between the vertices. We can see this is actually two types of graphs that's shown over here. One is with arrow and another one is without arrows. So is it okay? Yes, it is okay. It's just that, let's say the 6 over here, that it will only go from 6 to 3. And it can also go from 6 to 1. But can we go from 3 to 6? No, because it follows the arrow. It can only go from 6 to 3. When we look at the one that is on the left side, the graph, it is without any arrows. When it's actually without any arrows, it means that you can go from 6 to 3 or 3 to 6. So same for this whole graph. So tree are the restricted versions of graph because it goes from father to sons, go from up to down. It cannot connect directly from grandfather to grandsons, cannot connect uncle to nieces. So like in the tree, when we are actually talking about the tree over here, so let's say this is your grandfather and you have your father and this is your uncle. So now you're trying to, let's say your father, you have 2 sons and then your uncle will have, maybe 2 kids. So let's say this is a binary tree, but you remember that you will have 0, 1, or 2 nodes at most. So what says here is that you are unable to directly connect to your grandfather to the grandson. So it has to be, go from stage to stage and level to level. So a graph it doesn't have these kind of restrictions. It actually allows the edge to connect to any pair of vertices. It is most general of all data structures. It doesn't have a hierarchical form. It can be in any form. But let's say you're trying to arrange it, a graph where you try to connect between each of the nodes. It can be in any form. But of course, when you connect it, it has to be in certain kinds of rules that you actually set for the data. So graph is the most general of all data structures, can be employed for a wide range of applications that tree and list cannot help. When this one graph can be applied to the family tree, yes. But can the family tree, when you're using a tree, can it go to the graph form? Probably not, because tree will have the restrictions. So these are the applications that will apply where we have maps. Okay, we have electrical circuits, connections between components, physics and chemistries, bond between the atoms, and the problem modeling, partial problem development, solutions into different states. Well, later in the last slides, I'm going to share to you that what kind of applications that we can use to actually implement tree graphs and also the rest. So this is like the maps of the MRT routes that is in Paris. As you can see here, different stations that connected to each other, and it is really a lot. So if I try to ask you how to go from, let's say, this to this, and it actually looks very complicated, and there's any interstations that is in between. So how are you going to do it? What is the shortest route that to go from one station to another station? Well, if you are actually able to create applications that can actually help to calculate the shortest route, then it will be good. Well, of course, now there is a Google Maps that is able to do that. But now, since it's the COVID-19, that we are unable to travel, if you got a chance, let's say to go to Paris or to Japan, because in Japan, they have a lot of trains that you will need to go from one station to another station. It's indeed that the Google Maps can actually help you to determine the shortest routes that you can actually take. It's actually listed out what is the distance and what is the price and what is the time to reach from one station to another station. So all this, you can actually do it with graph. So that's why you need to learn graph and also understand about it. For a graph, it's actually defined formally as V and also E. V would be the vertices and E would be the edges. Vertices means that each vertex, okay, is also called as the nodes. Edge is the link between the nodes. Okay, so this 1, 6, 3, 5, 1, 2 are all here. This one is nodes. And the arrows here, okay, and the lines that is actually connecting between the two nodes here, we call it as edges. The one with the arrow, we know it as a digraph or directed graph that consists of directions, where you need to follow the direction. As mentioned just now, if this one is go to the tree, then it must be 6 to the tree. Cannot go from 3 to 6. If there's an undirected graph, it just only connected with the edges that have no direction, then the movement is go from 6 to 3 or 3 to 6. There's sparse graph, dense graph. Okay, sparse graph is a graph with a relatively few edges. And dense graph is a graph with many edges. So two vertices are adjacent if they are joined by an edge, which is node 1 and 2. Let's say here, this is 6. The adjacent nodes would be 3 and also 1, because they are actually the neighbor in the neighborhood areas of the 6. So it's 3 and 1. But if 1, then it would be 6, 2, and then 3, and then 7. because it has a line that connected to each other. But for 8, it only adjacent to 7. It's not adjacent to 2. Why? It's because there are actually no edge that connecting between the two nodes. Label graph. Okay, label graph, basically it is actually same as the directed graph that's shown over here. It's just that previously it don't have the weight or the edge, but now if here we can see that there's actually a value on the edge. So this is actually what we call as weight or cost. What does it mean by this weight of cost? If let's say here we are actually talking about from one destination to another destination, it can be the distance, like how many kilometers and air, or it can be the toll fees. Let's say you go from destination 6 to 3, then you will need to pay like 2 ringgit. So let's say you go from 6 to 4. How much that you need to pay? You can choose, okay, different routes. Let's say you go from 6 to 3, then go to 4, or you can choose from 6 to 1, then to 7, then to 15, or you want to go from 6 to 3, then to 4. It's your choice. Well, it actually depends whether you want to choose probably the shortest distance or the toll-free. A path, okay, is a sequence of distinct vertices that each adjacent to the next. For example, here, if you want to go to the 9, you go from 6, 1, 7, and then to 9. But you also can choose follow, okay, arrows here. You can go from 6, 3, 4, 7, then to 9, right? Because based on the arrows over here, you can only go from, or you can go from 6, okay, but if you go from 6, 1, 3 to 4, but you cannot go to the 9. The only way to go to the 9 is from 7. So that's why you have only one path here if you want to go from 6 to 9. A cycle is a path such that the last vertex on the path is adjacent to the first, as shown as below, 6, 1, and 3. So this one, it will become a cycle where you can go from 6, 1, then 1 to 3, 3 to 6, and then, you know, you just keep repeating here. So a graph is cyclic. It contains one or more cycle, otherwise it's acyclic.
My speaker. Wait. Okay, so another one is the undirected graph. Undirected graph is connected if there's a path from any vertex to any other vertex. When the graph is not connected, so we still can have connected subgraph of an undirected graph. They are called connected components. Examples here, we can see that this is fully connected graph, where each node they are actually connected to at least part of the nodes. And here is, there are 3 connected components where this one is one part, and this one is another part, and this one is another part, which is individual alone here. That's this one is called as a 3 connected components. Why graph traversal? In some graph problems, we need to visit all vertices systematically and do operations on each node, similar to the 3 operations. Like just now, when we try to do pre-order, in-order, and also post-order, we try to display the numbers of nodes that we also need to travel through the trees, right? So here is also the same. We need to travel to the graphs also. So graph traversal is the basic for the graph operations. But sometimes not all nodes can be visited in one pass. It's need more passes. For example, starting from node 1, okay, you can actually visit 3, okay, you can visit 7, and you can actually visit to 4, you can visit to 5, you can visit to 8, and visit to 9. Why? Because the arrows that shows up here is actually it's actually able to point. But can it actually go to 6? No, it's not able to go to 6 and 2 either. Why? Because of the arrows. 2 can only go to 1, but 1 can go to 2. So same for the rest, because there's no arrows that goes into the true. So given a starting node B, then the graph will start to travel in a systematic way to visit all the vertices that can be reached. So let's say given the V is actually 7, you can reach to the nodes, adjacent node, which is 8 and also 9. So in graph traversal, there is actually no root nodes to start with. Like in the tree, when we are actually in the tree form, we have the roots, right? Let's say this is a tree, binary tree that we have shown just now. It has the roots over here, where it always starts from the roots. For graph, no. You can actually start from, any nodes here that you can treat as the roots to actually start to form. So all nodes, they are actually equal. You can go from any nodes and it can travel in different patterns. But of course, okay, you have to think of that when you're actually doing something, you have to think of what is the structure of the data and how what do you want to do? So that is very important. Graph travels so can be applied in both directed and undirected graph. So if and only if it travels to all the vertices that the graph is connected. Of course, it's not connected, then you cannot go to that nodes, right? Only the one that is actually connected, like 3. Only 6 can be traveled to 3. 5 is actually so lonely over here. Then it is, you can't travel to 5 over here. And it also depends on the arrow. Let's say 6 to 3, you can only go from 6 to 3, but not 3 to 6. So if a graph contains a cycle, you have to prevent the algorithms to loop indefinitely as shown by the below, following the arrows here. So let's say you want to go from 1 and you go to 2. So here is actually without any directions. It is not a directed graph. So it's possible that, when you go to 2, then you go to 4, then you go to 3. If let's say you did not do anything, you just say that you just travel according to what. So it's possible that you go from 3 to 2, then 2 to 4, then 4 to 3. So it will actually keep going on infinitely. So what happened is sometimes you have to do the backtrack. So let's say you have visit 2, 4, and when you come to 3, you have to check back to the list that, let's say, I have actually visited 2, so I'm not going there anymore. Then you actually backtrack 2, 4. Then you continue to go to 5. So it would be have, the visit neighbor, mark, and also the backtrack. These are things that you would actually need to take note when you do the graph traversal algorithms. 2 methods to do. One is a depth first search and another one is breadth first search. Well, depth first search, it has backtrack, but breadth first search, we don't have. But how does the depth first search and breadth first search work? Given the same thing, you're starting from the same nodes. Depth first search and breadth first search can give you the different outputs by visiting the nodes, because the way of visiting is actually different between the depth first search and also the breadth first search. But here says that it will visit the same set of vertices. Let's say given the same set of vertices, then it will actually visit the same set. So now if you go into the depth first search, what it's going to do is it's going to go and travel to the graph as deep as possible before doing the backtrack. So let's say we start from A here, that it is actually a starting node B. It goes to the B. Right? So it has the freedom that you want to choose to the left or to the right. Okay, it doesn't matter. Why? Because this is a not directed graph. There's no arrow here that it must go to the B. It can also go to the I. But example here, I'm going to go to the B first. Then I go to C, I go to the D and G, and then I go to E. When I reach the E here, B and C I've already traveled before. So let's say I already recorded down that B and C have already traveled before. I'm not going into B and C anymore to actually avoid to actually go in to the loops infinitely. So what happened is it will actually backtrack. But before that, what happened is that you can see that patterns is go as deep as possible, travel until that it cannot move further anymore. So A, B, C, D, G, and E. Then what happened is it's going to be backtrack. Okay, go to the last node that's actually visited, which is from G. Then it goes to the F. When it comes to the F, it checks the neighborhood area, the adjacent nodes where A and G has already visited before, which is, we assume that it's actually in the record. So we do the backtrack. Because here we notice that I and H is not visited yet. It will backtrack, go through F, then it's actually go to D. Well, when it's actually come to D, it will also check that, oh, okay, here we have the adjacent nodes, C and also H. C I visited before already, but H no. So you will proceed to the H. H, well, it is, it does not have any further nodes. So you will go and do the backtrack. Come to the A here, it checks that, in the adjacent here, only left with the I. So it will go to the I here. So what happened in this case here when doing the depth first search is that it will go as deep as possible. Then it will try, when it cannot move any further, it will do the backtracks. So every time it's actually backtrack, it will check whether in the backtrack, it has any nodes that have never traveled before. Like the case that we have here, D, okay, you try the backtracks and check C and H. H is not traveled before, so I go to H. Then it's keep backtracking until all the nodes has actually visited before. So the visiting order will be A, B, C, D, G, E, F, H, and I as shown. In here, okay, the traversals, we actually use the green arrows to actually represent the deepness of the general tree. So A, B, C, D, and then E, then come down, go back to F, then H, and then the I. Is actually similar to the pre-order manner of the tree. So for the depth first search, it does not specify the visiting order. If I say we start with A, just now we go with B first, right? But now, no, I want to go to the I first. Well, you can go to the I. Then after you go to the I, you backtrack, you go to A. Though you go to the B, and then you go to C, D, and then E, and same thing. So there's no specific order. You can actually go from any directions that you want, but just remember that for the DFS, once you start to travel, if you go as deep as possible until it's not able to proceed, then it will do the backtrack to check the nodes that is not visited before. Next, we go to the breadth first search. Just now, for the depth first search, we go as deep as possible, right? So here, we don't go as deep as possible. We go level by level. So how can we say level by level? How we determine level by level? If tree, you can determine level by level, right? Because in a hierarchical way. So this is your grandfather. And this is your grandfather. So let's say you have two sons. One is your father and one is your uncle. And here, okay, we have your father will probably have 2 kids and your uncle also have 2 kids. So which means that here your father and your uncle is actually in the same level. So you and your cousin or your brother is actually in the same hierarchical level. But what about tree? Can we talk about layers? Yes. This is a layer 1 or A. Then what is a layer 2? So layer 2 would be the adjacent layer that is actually connected to A. So like here, I, F, and also B. Because only I, F, and B is connected to A, right? So this one we consider as a layer 2. Then for layer 3, it is this layer where it is actually circled in blue that is actually connected to B and also I, where it is E, C, and also G, because G is connected to F, E is connected to B, and C here is connected to B. So this one is considered as layer 3. Then we go to the layer 4. Okay, what happened? Okay, we go to layer 4 here, which is orange color, which is H. Then go to the outer one, which is the layer 5. So from here is that you have used a queue to simulate the visit one layer after another. So the arrow patterns again form a general tree, okay, like in the previous slides here. Different go from layer. So it actually depends on the depth of the tree itself. Or we can say here graph. Because if the graph is a lot, that means that, depth, it would be larger. So after we talk about how the graph is actually travels, we come to understand that from a graph can travel. So let's say the problems that we have here is the notes that shows over here is the name of the places where MD Awam, M Nawar, Ipoh, Kampar, and also Thermo. So these are the name of the places. I bet you know that where is Ipoh and probably Kampar. Okay. So these are all the places that's nearby to Kampar and also Ipoh. Now, if you want to get the shortest distance from Thermo to Ipoh, or Thermo to MD Awam, Thermo to M Nawar, and Thermo to Kampar. Thermo to MD Awam. So let's say the distance is 2. Okay, M Nawar is 20, to Kampar 8, and to Ipoh. If you want to travel from Thermo to Ipoh, there's actually different routes. Thermo, Kampar, Ipoh, or Thermo, MD Awang, M Nawar, and Ipoh, or Thermo, M Nawar, and Ipoh. So what you have to do is you want to find the shortest distance. So each of the edge here consists of the weight. So let's say I want to go from Thermo to M Nawar. I need 20 kilometers. But if I follow Thermo to MD Awang, M to M Nawar, I only need 14 kilometers. Because 2 plus with 12, you get 14. It's actually shorter than straight away from Thermo to M Nawar. So this will probably to be the best routes. If we look at the rules, okay, wait for the edges. It must be a non-negative real number assigned to the edges that reflect the dissimilarity between the two nodes, which is this similarity here we talk about is distance. So like for the weighted graph is that when a graph uses the weight to represent the distance between two places, and weight of the path, it is actually the summations of the weight of all the edges along the path. So let's say you want to go from Thermo to Ipoh. What is the weight of the path? You have to add on from these Thermo to Kampar, where these H8 here represent as the distance. Kampar to Ipoh, okay, 50. So the weight of the path from Thermo to Ipoh, it is 58. So shortest path would be the path that's with the smallest accumulated weight. So just now, as shown, thermo to M Nawa and thermo to, if you follow thermo MD Nawam to M Nawa, if compare shortest path, it would be 2 plus with 12. So to find for the shortest path, you can actually use the different algorithms. Okay, one here, the most popular, that's to find the shortest path is always Dijkstra algorithm. It's a greedy approach, okay, because it's always select nodes with the shortest distance to be expanded. This Dijkstra algorithm is the algorithm that created by Dijkstra itself. Because if you read on to Wikipedia, okay, it has a story that how Dijkstra create this algorithm is that he was actually accompanying his girlfriend to go shopping, that they went from one place to another places. So he found out that how can I go from one places to another places in the shortest path? So he starts to take out the papers and pen, start to draw all the notes. Then you do the calculations as well. So at the end, it comes up with this algorithm. So the objective, okay, is to find the shortest distance from a source node to all other nodes in a weighted graph. The input, it would be a weighted graph and a source node in the graph. So one day, when you go to shopping or with your girlfriend or boyfriend, if you try to save some time or save some distance or save some toll fees, then you can use this Dijkstra algorithm to find the shortest path. Okay, for the output, of course, it would be the shortest distance from the source node to all other nodes. Because you have one destination and you have the one that is in the place that you want to, all the nodes that you want to travel, right? So you must have to go from the source node to other nodes. This is an example, okay, that how the possible path that you can actually travel. Okay, next we go to the minimum spanning tree, MST. So a spanning tree of a graph, okay, it's just a sub-graph that contains all the vertices. A graph may have many spanning trees. For instance, the complete graph on 4 vertices. MST, okay, is an H-weighted graph, is a spanning tree whose weight that is no larger than the weight of any other spanning tree. So what does it use for the spanning tree is applications of MST include the design of computer networks, transportation networks, telephone networks, water supply networks, and so on. So this is an example that you draw out the spanning tree with a Prim's algorithm. Okay, so lastly, that you learn about all the things: tree, graph, deficits, traverses, shortest path, and minimum spanning tree. So what is to use in the real world applications? For tree, decision-based algorithm, and possible that to store possible move in a chess game. So just now, when we talk about AlphaGo in the speaker by Professor Tan from the NTU, before we go into deep learning, it's actually decided using the tree to actually sort out all the possible moves in the chess game. In this tree, we know that is what is actually happening in the middle. But when it goes to deep learning, we don't know what is actually happening in the middle. It's a kind of like a black box. But with tree, it's possible that you know. However, for tree here, it can be a very huge tree because it can be a factorial problem, as there will be many possible moves in a chess game. Okay, so another applications is a file explorer. I mean, it's very direct one. When you open your PC, you try to look into your files. It has like one folder is another folder, and this folder is another folder. So your file explorer basically is actually in the tree forms. Then we go to graph. Okay, for the graph, it can be a data organizations, recommendation engines, social media networking sites. Okay, every use is a node. like Facebook, when we talk about connections between friends and friends, it is actually using the graph, right? Because one, they actually have the adjacents, can have connect to all the mutual friends. Then if I say you want to connect, finding a deeper mutual friends, yes, it's actually possible that it will form in the graph. Depth first search, okay, solving the puzzle with only one solution, because that's the one that you're going to travel that and find the only one. Or you are finding strongly connected components of a graph. What about breadth first search? Breadth first search, it can be P2P network, BitTorrent, like when doing the downloads. I'm not sure whether you are using BitTorrent anymore. Probably you don't know about P2P network, but last time it's actually possible that you have uTorrent, BitTorrents to actually do downloads, where it downloads by finding the peoples that is near to you. So when you're actually finding the peoples that are near to you, what happens is that you will grab the source from these people that is actually nearby you and download it. It can be also used in the social network websites, Facebook, Instagram, like if you're trying to find the mutual friends, level by level. So let's say this is the first level of mutual friends, second level of mutual friends. So you can go and use the breadth first search to actually do the searching. Same for the Instagram. For Instagrams, you can have a mutual friends, right? Like when it comes up, this friend is recommended to you. Why? Because you have few connected friends together. And next, GPS navigation systems. Okay, it is also, you can use a breadth first search. Okay, then next one, we go to the shortest path. So what is the applications? Transportation problem, like in a parcel company, you try to save some oil money, or you're trying to be more efficient that can send more parcels. You can try to calculate, like from one destination to another destination, what is the shortest path to send the parcels. The next one, grab, calculating the routes. Okay, because every route, like this distance to distance is shortest, then how much that you would charge. Another one is the Google Maps. As mentioned just now, that in subways, okay, for travels, you can open just the Google Maps, key in from the source to the destinations. It will shows you like you need to take what from which stations, okay, which line that you need to change. And then you go for the IP routing like in the network. So you want to go from one network to another network. So you can use the shortest path and the flighting agenda. Well, for minimum spanning tree, what it can be used, because it's like the connections between the sub trees that connected. It will be used on landing tables, okay, network of pipes for drinking water of natural gas. So probably in the building, the constructions, how are you going to connect between the pipes? And also, if let's say the whole building, you have a gassing system. So how are you going to connect? Then land networks. So all these that you learn, if you learn about tree graphs and also searching all this, these are the real world applications that you're going to use. Okay, so now I'm going to share to you the codes that how you can actually do it. Just a few examples, okay, due to the time constraint here. Okay, first thing I'm only going to show you how you can actually do the graph implementations using STL. I believe last workshop, usually shown to you that how you can actually implement the linked lists and all queue and stacks using the STL library. So now if you want to implement the graph, you can use the STL. Okay, so let's say one thing you want to build a graph. First thing, what you need to do is you need to know that the graph, okay, which one is connected to each other, because you want to construct the graph, right? Okay, so let's say this is a graph. Okay, sorry, that I actually cannot draw it properly. Okay, but I just try to illustrate. This is a shape of a graph where 4 and 5, you can see here that there's two subgraphs. 4 and 5, another one is 0, 1, 2, 3. For 4 and 5, 4 is connected to 5 and 5 is connected to 4. Another subgraph is 0 will goes to 1. Okay, 1 will goes to 2, 2 will goes to 1, and 2 will goes to 0. For 3, it will be 3 goes to 2. How are we going to construct this graph? So the inputs that we provide here is the edge, because we need to let the know that which one is connected to which one. So after you actually construct, okay, given the instructions for the edge, that this one you are actually constructing with the edge. So what is the edge? Edge is in the struct where it has the source and also the destinations. All right, then you pass in the edge into the graph to actually construct the graph here. So what is actually the graph? You pass in two things. One is edge, one is end. So in the graph itself, okay, it is a class where it has a public, okay, public class where first thing you need to have an adjacent list. So this adjacent list is the, because you want to know that from one nodes, okay, what is the adjacent nodes? Okay, what is the adjacent nodes? So you have this graph constructor to construct the graph here. Pass in two informations. One is the edge and another one is the number of what? And is the number of nodes that you have. So number of nodes that we have over here is from 0 to 5, which is 0, 1, 2, 3, 4, and 5. That's total to be 6. Okay, I'm sorry if you hear something weird behind, because there's a constructions going on. When you come to the graph here, first thing is resize the vector to hold the n elements. And then you start to add the edge to the directed graph. So in here, based on the list that you have defined, okay, this is the one that adjacent list that you have actually defined. You can actually try to push back, okay, that's from the source to the destinations. So it's actually showing you that which direction that is actually going. Well, this is the directed graph. So if you're doing the undirected graph, then you'll be using this. Because for undirected graph, it can be in two ways, right? It's not just only in one way. Because this is a directed graph, so it goes on the one way. But here, okay, it goes on to two ways. Okay, so this one adjacent list is actually a linked list. But still, I hope you still remember what is a linked list. I think last workshop is already shown to you. So you run all this thing, okay, then you are able to construct this graph. So because you use the for loops to actually add the edges to the directed graph. Then after that, you construct the graph, you print it out. Okay, how do you actually print it out? You go to the functions that print graph. You pass in the graph also. Okay, this is the graph that you have actually constructed over here. And the number of nodes come in. So let's say C out 0, you get 0, 2, what? So based on the list, okay, linked list that you have actually created, you start from, okay, this is a V. V is where the vertices, which is a source that now we are actually in 0, right? So 0, you have to point it referring to the 0 nodes here. From 0 nodes, the one that is only pointed to is only 1. So that's why you see out, okay, you get the 1 over here. So of course, you only have 1 nodes, right? Then that's the end. You go back, then you go to the 1. You go to 2 because only 1 is connected. But when it comes to 2, it has 2 lists that is actually pointed to, which is 0, 1. So this is how that then you will proceed to 5, then it is actually the end. So this is how you can construct your graph using the STL. Okay, so I'm going to skip for the, or maybe I'll just show you, okay, very quickly, the breadth search and also the depth search. All right, so over here. So breadth search, when you do the searching, is based on the level by level. This one is also implemented using the STL. If you are interested to get more idea, you can go to this website. It's actually explained about how the breadth search is actually working. Okay, so now is same thing also, we have to define the address, which nodes is actually connected to which node. Okay, show to you here that this is a graph that we are actually looking at. So 1 is to 2, 3, 4, and 2 is to 5 and 6, 5 is to 9 and 10. So same, but 4, 7, 8, 7 is to 11 and 12. So for breadth search, we go from level to level. If you look at this, it will be easier. If you look in level to level, is we go from 1, then we go to 2, 3, 4, then 5, 6, 7, 8, then we go to 9, 10, 11, and 12. But how? In the code here, first you have to tell that which node is connected to which. Same like how you do the constructions. Then how many nodes that we have? Okay, we have 13, which is go from 0 to 12. And then we're going to build a graph from the given edges. Okay, build the graph. This is the edge that provide, right? So just now we built the graph, right? Same thing that we're going to use is we're going to construct the graph here. So this one is an undirected graph. So you can see, go from source to the destinations, and you also go from destination to the source. Right? So after you construct the graph, what you do is you need to keep track whether the vertex is covered or not. Because just now, if you remember that, okay, from the examples of depth search, that you're going to keep tracks to check whether this graph, is it you have visited or not, right? So same for the breadth search is the same, that you also need to keep track. So that's why, okay, you create a vector. Vector is actually something similar to the array, if you know what it's actually an array about, to actually keep track whether the vertex is covered or not. Then next, okay, we will create a queue for doing the BFS. So this queue here is considered as the STL, where you're going to create it. So for queue, I think last workshop that you learned about what is actually queue. It's actually connection between the linked list, like first in, first out. Okay, all that is actually related to the queue. Then now, okay, we start to travel using the breadth search to all the undiscovered nodes to cover all the connected components of the graph. So we will travel through, okay, the number of nodes. If the discover is actually false, means that it's not discovered yet. Okay, when they start to travel, let's say 1, it start to travel, is not discovered yet, right? So you change that to true, means that's already discovered. So you push it into the list here. Okay, so let's say drawing. So can I draw? Okay, so let's say you push in. 1 is now in the list. Then after that, okay, you go go in and recursive. So you bring in the queue here, you bring in the graph, and you bring in the one that discover list. So we go in and comes over here. So now we check if the queue is empty, returned. No, it's not, because we have 1 over here. Sorry. Okay, so we have 1 here. And then we go that DQ the front nodes and print it. V will be the queue of front. So what is the queue that we have front? Currently, we have 1. Pops up, okay, Q dot pop means that remove this one from the queue, okay, remove it, then see out the V. So V now here, I mean, temporarily, if we start it, okay, it's supposed to be 0, but I started with 1. So let's say we started with 1. Then when you see out, you get 1 here. So from the 1 here, what you need to do is one thing, okay, you need to check again whether it has the adjacent nodes or not. Okay, from the adjacent node, because you need to do it for every single list. If you still remember that when you print out in the graph, you're going to print out that which one is actually adjacent to each other, right? So from these adjacent, okay, you're going to go in and try to discover that whether the queue is discovered or not, whether the nodes is already discovered or not. If it is discovered that is actually true, else it would be false, then you try to push all the adjacent nodes into the queue so that it can go into the recursive graph, okay, and go in. So let's say here is 2, 3, and 4, right? 2, 3, and also 4. So it comes in here that V now is actually in the queue front, remove it from the queue and display it out V, where this is actually 2. Same for the 3 and 4. Okay, what happened here is that it's going to go in each of these nodes, check and put them into the queue here. So that's why you do it in the layer by layer, because you travel from one node to another node, then to another node. Then from the nodes here, let's say you travel to 2, right? Then you're going to check whether it has the adjacent nodes. Yes, so it will go into the queue at 5 and 6. 3, no, then it goes for the 4 and check yes, it has 7 and also 8. So that's why it can go from layer to another layer. Okay, so this is how that the breadth-first search can do, that it goes from layer to layer. So now we quickly go to the depth-first search. Okay, for depth-first search it's different. Definitely, it's actually different from the breadth-first search. You can see that the structure is already, the arrangement of structure is really a little bit different, but same. You need to construct the edge and you need to construct the graph. But when it goes into depth-first search, okay, which is this part, what happened is once you have actually discovered the nodes, you put it as true. Then you just print it out. Same that it goes, okay, check on the edges. But just the problem is that when it comes in, it will keep travel. Okay, instead of trying to keep track on the list of the adjacent nodes. Just now, like in the breadth-first search, you have to keep track on the queue, right? But depth-first search is no. because based on the how you construct your depth search, the algorithm of depth search, you don't need to keep track on the queue. What you do is you go from 1, 2, 3, 4. Then you will backtrack. You go to 5, backtrack, go to 6. Then backtrack, okay, go 7, 8, and more. So the arrangement of the codes in the depth search and breadth search would be different. I'm not going to explain, okay, in details over here that, you know, how to keep tracks all this, but just the concept is that depth search, you go into deeper and deeper, but for breadth search, you go from layer to another layer. Okay. The last one that I'm going to show is the shortest path using the Dijkstra algorithm. Okay, for this one, right, let me show you. Okay, so let's say this is a graph examples that we have. Maybe okay, this one, right? So this is a Dijkstra shortest path that I get from free code camp. Okay, this slides will actually show it to you, but if you're interested, then you can go to this website to actually to read more about it. So this is a graph that we have how many nodes? 1, 2, 3, 4, 5, 6, 7. So we have 7 nodes, which is from 0 to 6. And it's actually carrying the weights. Because you see the edge, it has numbers, so it has a weight itself. So for the Dijkstra algorithm, to get the shortest path, okay, what you need to do is you need to have 3 things. Okay, first thing is create the shortest path travel set to keep tracks of the vertices of the shortest path of the tree, which means that there would be minimum distance from source, okay, to the destination. So initially, this set that we actually keep would be empty. Second things from the algorithm is assign a distance value to all the vertices in the input graph. So initially, it would be infinite because let's say here 0 to 6. What would be the distance? Initially, you don't know, right? Because you haven't checked on which one is the shortest path. So we just initialize it to be infinite. But for the source itself, it would be 0 because it's the one that will pick up first. So when go start to travel, few rules that follow is pick a vertex U that are not in the set and has the minimum distance value. Then you include the U to be the set. So update the distance values of all vertices of U. Then to update, check on the adjacent vertices. So with the adjacent vertices, you need to calculate, okay, the total path that you have actually able to travel to the destinations. Then you pick the one with the shortest. Okay, so how this one works. So let's say over here. Okay, for this one. Initially, if you still remember that initially, okay, you have this set to keep tracks, and then initially that all the distance is actually infinite except the source here. So source here, we start from 0 and the rest will be infinite. Let's say from 0, I'm going to go to 1, 2, 3, and then I'm going to go to 6. It's infinite. We also keep tracks on the unvisited nodes. And this is the sets that we will have to keep track. We have to check that, okay, which node that we have actually traveled. So first, if you start from 0, it goes from 1, okay, and then it also goes to 2 because the adjacent node that we have is 1 and 2. Okay, so we change the distance from 0 to 1 is 2 and 0 to 2 is 6. So here we're going to apply the third steps is we're going to check, okay, which one would be the shortest. Because from 1 to 2 now is only have one roots. It carries only one weight, right? So we compare. 2, if compared to 6, is the shortest. So we take the roots, okay, 0 to 1. So we put the 1 into the set. So which means that 1 has already been traveled and we know that it is actually the shortest path. So when we come to 1, we have to take notes, okay, we have to update on the adjacent node. One adjacent node is number 3 here. So it only has one adjacent node, it's actually 3. Okay, the distance, it has to be from the source to the destination, which is 2. We have to plus with 5, you get 7. Okay, so now what happened is we can compare between 6 and 7. So 6 and 7, of course, 6, it is actually the shortest. So we put the 6, which is 0 to 2, in the set here. So in the unvisited nodes, the set here, we have removed 0, 1, and 2. So we go from 2, okay, we check that 2, it has the adjacent, which is 3, but in the list here, 3, we already get the information that it has 7, but I have from 0, 2, and 2 to 3. So which one would be the shortest path? That's why we have to make the comparisons, because 0, 2 to 3 and 0, 1 to 3, it can reach the 3 also. So of course we need to choose the shortest one, right? So that's why we choose the one that's 0 to 1 and 1 to 3, which is 7. Because from 0 to 2, 2 to 3, the distance is 14. Is actually, we can say the distance is actually longer if compared to 7. So that's why we choose 0 to 1, then 2, 3 over here. When we look at 3, we also need to check on the adjacent, because now it's actually in the sets. When it's actually in the sets, we have to check on the adjacents, which is node 4 and also 5. Go to the node 4, okay, the distance from 0 to node 4, it is 17. Go from 0, okay, to 5 through node 3 is 22, because 15 plus with 5, 20 plus with 2 is 22. Again, here we choose that which one is actually the shortest, which is actually 4, 17. Okay, it's actually 4, so we put 4 in the set, shortest path set. Okay, then for 4, it has 5 and also 6. Okay, 5 and also 6, but we choose the one that is actually in. Okay, we go to 6 first. We choose this one because if compare that 5 and also 6 from the source here, okay, the distance, if let's say here 5 plus with 2, 7, 10, 7, 17, then plus with 6 is 23, right? But if here, this one, okay, come over here is 19. So we go to the 6 first. So when you reach the 6, okay, the distance will be 19, and we will stop over here. But we still have 5 that is not traveled yet, right? Okay, because we're going to put the 6 into the shortest path list. And at last, we're going to go to and check on 5. So for 5, it has 3 ways. Okay, one way is go from 0, 1, 3, and then from 3 to 5. So for this one is 2 plus with 5 plus with 15, we get 22. The next one is 2 plus with 5, then plus with 10, then plus with 2, then plus with 6, which is we go through the 6. For this one, the distance will be 17, okay, 19, then it would be 25. Okay, if that you travel through route through the 6, you get 25. The third path, okay, 0 to 1, then to 3 to 4, and 4 to 5, that you get it as 24. So compared with the 3 roots, this 2 plus with 5 plus with 15 is the most less, which is 22. So that's why you choose to travel 0 to 5, you go from 2, 1, okay, then to 3, then to 5. Instead of, choose the other path over here. So this is how the Dijkstra algorithm works to find the shortest path. So to explain and the codes, okay, and also the concepts, you can check on these 2 websites. So now we're going to look at the codes. How does it get implemented is, first thing you need to define your graph. Okay, we put it into a 2-dimensional array. So for this graph here we have 6 nodes that it's actually connected to 6. It's possible that connected to 6 nodes, right? So this first, we say it as row. We call it as is referring to the first nodes. So this one is referring to second node, third node, okay, until the 6 nodes. 1, 2, 3, 4, 5, 6. Oh, yes, 7 because we're starting from 0 to 6. Okay, and here, what is the value inside each of the columns here? So for this one is represented as 0 nodes, and this is actually recording down the weight of the edge. So 0, 0 is itself, so it's 0. But here is 0, okay, to 1. 0 to 1, the weight is actually 2, so you put 2. So 6 is 0 to 2, so this is actually the weight. So same for the rest. You construct, okay, give the informations about the weight, then you go to you call the functions. Okay, so this is the functions where it's a bit long. Okay, you pass in all the values, so you can see that you construct this V. So this one is hold the shortest. Okay, and then you have these SPT sets where you're going to keep the information to see whether it's the shortest. So like the one that shows you in here, which is represented as this one. Okay, and then initialize, okay, all the distance as infinite, and this SP sets, we put it as a false. So each case, whatever that's, let's say here, 0 if it's not inside the set. So here we put it as a false, but if it is inside, then we put it as, we change it to true. So this is how that you will do the records. And we're going to start from the source where it's always 0. So this is actually the for loop to find the shortest path. So first thing we're going to call, okay, that's, we're going to pick the minimum distance from set of vertices. Okay, so if you go to the minimum distance, if we look at the minimum distance here, what happened in this? Okay, I'm not going to go into details, but I'm going to briefly explain that what happened in this, that it's going to record down, okay, for the vertex, which vertices that will give you the minimum distance. So it goes through based on the source nodes that provided. Okay, then it will do the calculations. It will check whether is it inside the set already or not, and is it less than the minimum distance. Well, all these, if the conditions is actually true, then it will record down the minimum distance and check on the minimum index. So then it will return. Okay, if it returns. So what happened if, let's say, it is already successfully traveled, then you would change it to it's already been processed. So like the one that shows in the here, that's if this is already success, let's say the 0. Go to the first one. So 0 here is already success, that is go through, so it will change it to true. Because initially we set it as false, right? So now you go into, update on the adjacents using the for loops, because you have to check, let's say in tree, how many for loops that you have, 1, 5, 2, and also 4. So you update on the distance. And at last, you print out the solutions. So this is the solutions. If you check back, okay, if you compare it with the slides that we have over here, 0 to 0, it would be 0 because it is actually itself. 1 to 2, okay, 0 to 1, sorry, 0 to 1, okay, the destination is actually 2. Okay, I have to show the last slides here. Okay. 2, okay, 0 to 2 is 6. Then 0 to 3, it is 7. 0 to 4 is 17, 0 to 5 is 22, and 0 to 6 is 19. Okay, so this is how, this is the codes for the Dijkstra travels to find the shortest path. Okay, so I think that's the end for the workshop number 2, where we actually talk about the trees, talk about the graph, and also what kind of applications that it actually can be used if you know about this. But tree graphs and all this is it can be developed in a recursive way, or it can be in an iterative way. So it depends on how you're going to apply it. All right, so any questions for this workshop? Okay, if there's no questions, then I think that's the end of this workshop. So one last time, is there any questions about this workshop? I mean, any questions about the trees and also the graphs and all that? No, okay. Still 消化中. Yes, for this, what my suggestions for you is, if you really want to study and go into the trees and also the graphs, right? It's better that, okay, these codes, I'm going to share it to you. Not to you, but share it by the committees, the organizing committees that will share it to you. So probably if you have time and you are actually really interested in, what you can do is you can try to go through every single line of codes and keep track on what is the input, if let's say put in the inputs, and what is the outputs that you're going to get. So okay, so no more questions. If no more questions, I guess we will stop over here. And thank you for today. 谢谢大家。我觉得应该会很闷吧，这个东西。所以如果没有什么问题的话，感谢大家。Take care. See you probably in the next workshop, because in the next workshop, what the workshop will be, okay, it is on hashing table, and if I'm not mistaken, it's on searching. So how merging or searching, I'm not sure, but definitely it will be different topics from the workshop too. Okay, so thank you very much. Goodbye. Take care.